and it is a cooperation between the University of Hamburg, Cambridge University, and the research spin-off Baqend. We are both from Hamburg and also work at Baqend, obviously. And the whole idea of speeding up web applications through caching originated back in 2010 as a research project at the University of Hamburg and has since evolved into an actual product that is being developed by Baqend that was founded in 2014. But let's go right into the topic and start with a quick motivation and a high-level overview of how we do this caching. Then we cover the main challenges that we needed to solve along the way. And finally, we will look at the real-world application of this technology. Okay, let's start. Should be ready in a second. There we go. Those were 9.3 seconds, which is the average loading time of an e-commerce website. And even though we all know how annoying slow-loading websites are, it's quite astonishing how much impact they have on businesses. For example, Amazon found that if you use 100 milliseconds of load time, you will end up losing 1% of revenue, which for Amazon amounts to $1.3 billion a year. Or a similar study by Yahoo who found that 400 milliseconds means they would lose 9% of their visitors. Or even Google, who found that if they display more search results but need 500 milliseconds more, they lose 20% of their traffic. Now, obviously, page load time is money, and we as computer scientists ask ourselves, what are the technical bottlenecks when loading a website? To answer this question, we have to look at the state of the art. And there are actually two bottlenecks. So if we have a user on the left here, accessing a website hosted on the server on the right, the first bottleneck is always that the website has to be assembled in the backend, with some database queries, and this causes processing overhead. And the even worse bottleneck is the one that we have to transmit all these resources over the network to the client, suffering from high network latency. And with over 100 resources for an average website, this network performance becomes a real performance consideration. And this is nothing that you can really fix by buying a better internet connection, because if we look at this study by Google, if you increase your bandwidth of your connection above 5 megabits per second, you really don't get any better page load times. But on the other hand, if you manage to decrease your latency, then you get always a linear decrease in page load time as well. So in simple words, twice the throughput leaves you with the same load time as before, but if you can cut the latency in half, you really get half the load time. So obviously we need to do something about latency. And the only real option that we have to decrease latency is bring our data closer to the clients. And this is where our solution comes in, because we leverage the existing HTTP caching infrastructure to not only serve static data files, but also dynamic data like database records and even queries. So that our users only have to access a nearby copy of the data and therefore get all the resources extremely fast. And as a side effect, we also have less processing in our backend. So, because we do not only cache static files that do never change, but also dynamic data and queries, our main challenge is to keep all these copies, global copies, consistent. And this will be the topic for the remainder of this talk. And this is also the technology that we have implemented into our backend as a service. And before we go any deeper into how we do this, we quickly look at what this means for web applications in practice. So for a benchmark, we implemented this really simple news application on our backend as a service with the caching technology, and also on some competitors like Firebase, Parse, and so on. And if we look at the results, globally loaded from different locations all over the world, we can see that backend loads consistently within 0.5 seconds, and on average 15 times faster than the competition, which apparently doesn't even fit on this slide here. Okay. But now we want to talk about the how we do it. So the main challenges that we needed to solve. To do this global caching of dynamic data, we had three main challenges. The first being cache coherence. So we have to keep dynamic data up to date in expiration-based caches. The second will be that we have to do invalidation detection. We need to know when do query results change. And the third being TTL estimation, because we need to optimize our cache hit rates, obviously. So let's start with cache coherence and look at how normal traditional HTTP caching works. We have our client on the left, and he is requesting a resource from the server on the right. And this response sent from the server will then be cached in all intermediate caches. Both the invalidation-based caches like CDNs, but also expiration-based caches like, for example, the browser cache. And those caches will deliver this resource until the time to live, the TTL of this resource expires. So the real problem comes in when we have dynamic data and another user or process changes the resource in our server. Now the server is the up-to-date version, but all our clients and the caches in between have a stale, so outdated version of the data. Now, this is where our cache coherence strategies comes in. We have two strategies, one for invalidation-based caches, because those are the ones that we can control from the backend. So we simply tell this cache that there is new data that it needs to fetch. But there are also these expiration-based caches that we cannot control from the backend. Only the client itself can control these caches. So we need a way to tell the client which resources it can take safely from the cache and which resources it needs to revalidate. And this is where we take the ID of this resource, then we hash it and put it into a probabilistic cache data structure called a counting bloom filter, here on the bottom. And then we send a flattened version of this bloom filter to the client. The client now, whenever he wants to request a resource, looks into the bloom filter, and if the ID is contained, it knows that it cannot take the version from the cache, but needs to do a revalidation request that will then hit the CDN or backend and will update all intermediate caches along the way. And once the TTL of the old stale data has expired, we can remove the ID from our counting bloom filter. Now the great thing about this bloom filter is that it's extremely space efficient. So to give you a feeling of that, if we have a bloom filter with 20,000 distinct entries and a false positive rate of 5%, this bloom filter is only 11 kilobyte small. This means we can transmit it in a single round trip for the initial congestion window of TCP. So when the website is first loaded, which is just a one round trip to send this bloom filter. So this whole cache coherence strategy gives us certain consistency guarantees, and the most important one is delta atomicity, where the client can specifically define this delta. So this was the quick overview of cache coherence, and now I will hand over to my colleague Wolle for the remainder of the talk.
Yeah, thanks Eric, and servus everybody, I'm Wolle, and I'll be the host for the rest of the talk now. So Eric basically pitched the problem of slow websites and also introduced the salvation, which is storing copies all over the place. And also he outlined the three challenges that we basically see here. And the first one is cache coherence, which basically amounts to the question, how can the client know which copies are good to use and which need to be revalidated? So for which data do I have to go all the way back to the backend? Now I'm going to talk about invalidation detection, and that basically is the question, how can the backend know which data has become stale? And to illustrate the issue here, just consider like Amazon.com and you're browsing products, and what you see there is maybe something like a query, give me the most popular products that are in stock and match my search query. So you have this query and you store it in the cache somewhere, and to spot cases where this query becomes stale, you have to consider every single update that hits your database and check for this cached query. Does it add something, or does it change something, or does it remove something from the result? And that's pretty complex to do if you're caching like thousands of queries. And what we do here to make that feasible is basically we have our application server, and that does all the client communication and receives read, write, and query stuff and like that. And then we also have a separate system that does only this real-time query matching, and we call it InvaliDB because it basically invalidates database queries. We build it on Apache Storm, and it's vastly scalable. And what happens here is that every time a query is cached, InvaliDB gets this query, and then from this point onwards just maintains the result. And InvaliDB also gets every single write operation that happens anywhere. And every time a write operation affects a query result in some way, InvaliDB sends a message of this. So something like, hello, query XYZ has become stale, to the application server, and that in turn can then update the bloom filter and purge the invalidation-based caches, so that clients know, okay, query XYZ is now stale, I need to execute it again at the backend. And as a pretty neat side effect here, InvaliDB can not only just output the information that a query has become stale, it can also give you the change delta. So what we have here is an additional API based on WebSockets, where clients can subscribe to a query and then they receive the initial result, and whenever there's a change, they receive the change delta. So they can really stay on top of their critical data set in real time. And it's performing pretty nicely. So on the left here you see that InvaliDB scales linearly, so the sustainable matching throughput, with the number of nodes we employ for matching. And on the right you see that the latency that is exhibited by the system is pretty much consistent across configurations. So whether you have a small cluster or a huge cluster, doesn't really matter, you always get the same performance. And that's the vague idea of how we do invalidation detection. And that basically leaves you with a question, okay, I have a query and I put it in the cache. For how long should I put it in the cache? So, and that's TTL estimation, and the obvious trade-off here lies between short TTLs and longer TTLs. And if you have a short TTL, the merit of that is basically that caches evict themselves after a very quick time, and so you have not as many invalidations because stuff just moves out of the cache anyways. If you have longer TTLs, things stay in the cache longer and therefore have higher probability to become stale, so that we do something about that by sending invalidations and putting them in the bloom filter. But on the other hand, we have higher cache hit rates with that, so we need to do something that decides whether a query has a long or a short TTL. And we have several approaches here, and the quintessence is basically trying to get realistic TTL so that we can use our bloom filter space optimally and don't have to perform as many invalidations. And we also try to spot queries that are probably going to be invalidated soon anyway, so the ones with a minimal TTL, so that we know, okay, this query is write heavy, don't cache it at all. It's not worth it. And another aspect of this is also that we can choose between two different kinds of representations for a query result, because you could either store the fully blown result with, a product list with product name and product description and everything. That would be the object list on the right. That's pretty cool because the client accesses the cache. The client directly in a single round trip gets the entire result, so everything he needs to know. However, if you update one single product in your result, even something that doesn't really relate to the matching condition of the query, then the result gets invalidated because the result contains the fully blown objects. If you instead just cache ID lists, so the ID of the matching objects, then you get less invalidations, but obviously clients need to fetch the ID list in one round trip and the objects in a separate round trip, so that's the trade-off here. At the moment we have a rather simple cost-based decision model that weighs expected costs against one another. However, we are currently working on reinforcement learning here to basically get more informed decisions. And that's the scientific part of our talk now, but we're actually an industry paper, so I'm going to talk about how we put that into practice with Baqend for the remainder of the talk now. And first, maybe a short overview of Baqend. So Baqend is a Baqend as a service, and we have a polyglot backend, so several scalable databases that are basically, encapsulated behind a unified API. And we do all this fancy caching stuff we talked about here, but you as a customer don't really need to know any of that because you have a simple HTTP interface, and our clients are basically anything that speaks HTTP. So we are hosted completely on AWS, and are using Fastly as a CDN. And as I just said, clients are basically anything that is able to communicate through HTTP. Yeah, and if that sounds fancy to you, you can just build your own website on Baqend. We have a dashboard, we have a command line interface, we have REST and WebSocket APIs and a pretty sophisticated JavaScript SDK. But chances are you just say, okay, all nice and dandy, but I actually do have a website and it's not as fast, and I like you to speed that one up. And actually, we have something for that too, because we thought it might be a use case that you actually want your website fast. So we built the Baqend speed kit, and it just it just basically works with a service worker. That's a background script that's executed when you visit the page, and it basically redirects your requests that are targeted for your slow web server to instead access a fast copy of your website on the backend infrastructure. So you can just include your the service worker script in your website with like 3 lines of code, and we also do have a WordPress plugin, and then it's just becoming fast, and you don't really have to do anything about that. And as a demonstration, we have something done here with the VLDB website, and as you can see on the left, the vanilla page loads within 1.5 seconds, and our enhanced SpeedKit version loads within 0.2 seconds, and I hope the video is running. Well, not so much. Anyways, just imagine something's happening here. It's beautiful, I wish you could see it. So, okay, that's basically the end of the talk now. Just sum things up briefly. We implemented the Questor architecture and put it in practice with Baqend, which is a startup, and you can visit the website baqend.com if you don't really care about what I'm saying and just want fast websites. If, in contrast, you really care about the details and want to know more, then I suggest you come to the poster session or have a beer with us later, and we're going to talk about everything you want to know. So thanks for your attention, and I think we're ready for questions now.
What happens to the latency on the right side? Do you update all of these caches and filters synchronously with the right?
No. It's just you write to the backend, and then basically, Eric talked about the delta atomicity. You specify something like, okay, I want 10 seconds. That means that the client asynchronously refreshes the bloom filter every 10 seconds. So you know that you may see stale reads that are 10 seconds old, but no older than that, so that's not synchronous.
For the CDN, we have a end-to-end latency of 200 milliseconds, so global invalidation within that time.
That's a naive question. The first time the website loads, what happens? Because as I understand, the cache is good for subsequent.
So the first time you load the website, you will fetch obviously the HTML and also the bloom filter, so you know which assets and which resources you can take safely from the cache, and then you go from there. And if you also want to cache HTML and all your assets, we have this service worker that can cache HTML, and that will fetch the bloom filter, which is really small, before that, and then decide on whether to deliver the HTML from the cache.
So it's not any slow?
No.
Not at all. It's significantly slow.
Yes.